So let me formally start the webinar. So welcome to the next webinar in the Best for Water Systems Research seminar series hosted by the Center for Water Informatics and Technology at LUMS. It's been a great series so far, and in fact, this is the last talk of the 2021 part of the series, and it gives me great pleasure to introduce the speaker, Dr. Brian Fath, who is a professor in the Department of Biological Sciences at Towson University, Maryland. And he's also a senior research scholar in the International Institute for Applied Systems and Analysis in IASA. He has published many research papers in his field, which is primarily ecosystem ecology, environmental science, human ecology. He has co-authored many books and has been the editor-in-chief for Ecological Modeling Journal of Elsevier for 11 years from 2009 to 2020, and he is also serving as the editor-in-chief for the journal Current Research Environmental Sustainability. So it's a pleasure to have Dr. Fath here with us, and he's going to be speaking on a topic which is very much in line with the seminar series, where we like to discuss the different aspects of systems analysis, especially in the water systems, the water systems discipline. So, all right. So just before I say something else, just let me hand over to Dr. Abubakar to say a few words to introduce the session.
Thank you, Talha. And I think once again, this is a special moment for us. This is a moment of honor for us to host Dr. Brian Fath. I was actually looking at the abstract that Brian sent, and I was really struck by one of the sentences that he wrote in there, that he especially wanted us to pay attention to that these reductionist mental models in which we treat living and environmental systems as if they are machines. And this is an idea that has really bothered me for a while. Maybe for Brian, if I can take a minute, maybe you would know that in the Indus Basin in Pakistan, when the British developed the canal systems colonies, they actually treated these canal systems, as you would know, these are socio-hydrological systems, as if that these are machines, and they actually used the terminology of a food production machine for this. They actually use the analogies of thermodynamics. They use terms like duty as if it is being used for a machine. So essentially treating this very fascinating development of irrigation within the basin as if that they were solving this food crisis, but using this very sort kind of a machine analogy. And the repercussions of that we see even up till this day, where this kind of a narrow approach towards thinking of this irrigation development as some sort of a mechanical development was quite limited. I think moving onward, this kind of systems thinking, this holistic thinking, where we kind of couple things together and sort of, so this again is very much near to our heart. Our training is basically from this control engineering kind of perspective, and from this we see this kind of a natural sort of connection to this holistic thinking. And in our own work, together with Talha, we have actually paid a little bit of an attention to exploring ideas of sustainability versus, for example, stability, and co-evolution of natural systems with social networks. And one of the themes that has been running throughout this series is that of social hydrology. So I think your talk is very much in line and very pertinent and very timely as we are exploring all of these concepts, especially this idea of a non-mechanical kind of a perspective, this idea of thinking beyond the machines, these river basins and these canal colonies as living systems, as sentient systems, and also your very deep work into the very idea of sustainability. what does it mean? How is it different from stability, say, or how is it different from other sort of concepts? So this is something that I'm very much eager to learn from, and looking forward to your talk and learning many things from this. So over to you, Talha and Brian.
Mhm. Yeah, thank you, Dr. Abu Bakr. And just before I hand over to Dr. Fath, just let me tell the attendees that so you can use the Q&A feature, the button that you can see at the bottom ribbon of your screen. You can type in your questions at any point, and we'll read them out to the speaker at the end of the talk, and he will be able to answer your queries. So yeah, so looking forward to the talk. And yeah, Brian, so over to you, please.
Okay, great. Thank you for the invitation. Thank you, Tala, for the introduction, and Dr. Abu Bakr for also the setting the stage very nicely, because I'm going to talk quite a bit about the philosophical side of sustainability. So the title of the talk is Systems Analysis of Embodied Water, Implications for Sustainability, but probably the first 2/3 of the talk will be about some of the more conceptual and philosophical sides of sustainability. And then I'll move into a couple of case studies that using network analysis to really look at the embodied water of different socio-ecological systems. So quite a bit of this work is taken from our recent book called Foundations for Sustainability, which is co-authored with Dan Fiskus. And so I encourage you to also look into that if you're interested in these topics. When I give any talks these days, I like to start by giving a little bit of recruitment or advertisement for IASA, particularly for the Young Scientist Summer Program, which Tala is very familiar with. It's actually, we're approaching our 45th year this coming summer in 2022, but that banner is a couple years old. It's a great opportunity for PhD students to come to IASA and work with IASA scientists. It runs for 3 months during the summer, and you would get funding from the national member organizations that are part of IASA. A date to keep in mind is January 14th, which will be the deadline for this coming summer's applications. So if you have any other questions about that, please feel free to reach out to me for this program. Okay, so let me just jump into some of the ideas I have about sustainability. And first, as we're aiming or reaching for sustainability, what are the impediments, right? What is getting in the way? I'm maybe it's Malthusian, but I'm a strong believer that population growth is really one of the key drivers, if not the key driver. And as long as human population is growing, it's only going to make it more difficult for us to reach some sort of sustainable system. Second of all, I think that in a complex system cycle of multiple stages of system dynamics, that we're really focused only on the growth stage. And nature works much more in cycles, but our industrial systems are always about more and bigger and so on, and that's incompatible, I would say. Most of the energies that are driving our systems nowadays are non-renewable energy sources and non-renewable materials, so that also has its problems. And as a result, then we're really impacting the major biogeochemical cycles: carbon, nitrogen, phosphorus, hydrological, of course, and that's then showing up in the symptoms that we see that we are trying to deal with. And then lastly, I would say is this kind of lack of a conservation awareness and ethic. It's just not really built into the model that we have, the mental model, to think long term, to think in systems. And so we tend to do short term thinking at the wrong scale. And I'm very much for promoting more systems thinking as a baseline move for that. Also then keeping in mind that as human pressures on the planet have increased, we went from being what has been referred to as an empty world, where the human economy and the human imprint was actually fairly small compared to the ecosystem and the ecosystem services that we received. And therefore, whatever humans did could very readily be assimilated by the environment without too much difficulty. But again, as we've expanded, I think we're reaching 8 billion people this week or next week. I've read, of course, the estimates are a little bit different, but very soon we're going to, before the end of the year, I believe, we'll reach 8 billion people. And our footprint is everywhere, whether it's, PCBs or microplastics They're from the Arctic to the Antarctic, and we really have engulfed the globe with one species. And part of that is it's happened very rapidly on an evolutionary or ecological timescale that we haven't kept up with them in terms of how we think about things. Our customs, our ethics, our religious patterns have not had a chance to adapt to them. And I give these two pictures as an example, is that, if you look at ancient artwork, this is an Egyptian artwork where farming was revered and respected, and the basis for life, and it was such a part of their thinking. And nowadays, the way we grow our food and our cattle is kept out of sight, out of mind. We don't want to know how it's grown because we would actually be appalled by it. And so to be able to integrate an ethics that is consistent with how we actually do things is very much lagging right now. Well, Donella Meadows, lead author of the Limits to Growth book, which is extremely important, also published another book later about how you change a system. What are the leverage points in affecting system change? And her number one up the idea was the power to transcend paradigms. This idea that you need to think differently, that you need to approach things differently. And so this is really the big picture side of things. It might not answer the question of how you live your life daily differently, but it's to really encourage different ways of thinking. And again, systems thinking is primarily that. So let me start with what I think our dominant paradigm is, and then offer some alternatives to that. And we refer to the current dominant paradigm as ARMS, analytical, reductionist, mechanical science. And there's some pathologies that we think actually stem from this. And some of the problems that we have can't be solved by just continuing to apply this, more and more, that we need to rethink it. One of those very basic things is what we get wrong about environment, how we see the environment. We think of the environment as something separate from the system of study, whether it's a species or a nation or a city, a water system. We think of the environment as out there somewhere. We look out the window, well, that's the environment. And we've fragmented ourselves from the environment. And yet we know that we are intimately connected with it. And there's a great quote by one of my favorite authors, Wendell Berry, who made the point that, the concept of outside has become simplified as the environment. That is what surrounds us. And once we see our place, our part of the world is surrounding us, we've already made a profound division between it and ourselves. Therefore, we've given up the understanding and dropped it out of our language and so out of our thought that we and our environment create one another, depend on one another, and are literally part of one another. That our land passes in and out of our bodies, just as our bodies pass in and out of our land. That we are part of one another and so cannot possibly flourish alone. So we know that the environment is not just out there. We drink the environment, we eat the environment, we collect resources from the environment, we give things back to the environment continuously, right? I mean, we're carrying the environment in us all the time, and we need to somehow eliminate that fragmentation. So therefore, rather than having this old dichotomy, recognizing that we are actually the focal point, the focal system at some scale of two separate environments. We're taking in from the environment continually to construct us, but then also generating output into that environment. Here's just another depiction of that using network science, which I'll talk a little bit later, and also then recognizing that we have feedback, that our output can actually come back in and influence us in more complex pathways. So it's really inseparable from the environment. It's part of two environments. And so what we suggest is, rather than having separation and fragmentation, which leads to the tragedy of the commons, that we want to understand life and environment as one unified system. And we try to use that term in the book as life environment. Whenever we refer to life, it's life environment. There's not life independent, which I'll say more in just a second. And we've actually constructed what we refer to as a hyperset equation, which really makes this explicit, because this life environment conglomeration essentially is combining together environment at the largest scale, and within environment are ecosystems, and within ecosystems are organisms. Within organisms is the environment again. Again, the minerals and the energies inside our bodies is the environment, right? So when environment shows up at the outside and the inside of this equation, it can't be fragmented. Okay, so what about life then? Like, what does the arms paradigm say about life? It says that life is something that reproduces and replicates and metabolizes, and we can think of a single cell that could have all these necessary aspects to be alive. It could be more than a single cell organism. It could still, just an organism out there. Biologists love to study these different kinds of organisms. But again, that's a fragmented, separate understanding that we refer to as discrete life. It's important. It's part of the living world for sure, but it's the organismal reductionistic view of things. When again, in reality, that organism is only alive if it has environmental and ecological interactions. It needs to eat, it needs to mate, it needs to defend itself from predators and so on, that it's continually interacting with that. And we know this, right? Here's some artwork that showed up in our book about how any organism is really made up of all the organisms that it eats and so on. So if we could actually see the food webs inside ourselves, we might again appreciate this better. But in terms of our discrete life model, what we are proposing is that recognizing again that an interacting ecological community and its environment is actually an ecosystem, and that sustained life happens at the scale of the ecosystem. Almost by design, individual organisms have finite lifetimes. That's part of the evolutionary genius, in fact. But ecosystems can be sustained life, and at that scale is how things continue. So our proposed correction here is to recognize that this dominant mainstream view is not really correct, right? So life is not only an organismal property, it's not an objectified or material phenomenon, but in fact, life is relational, distributed, non-localized, integrated, and so on. And so we're promoting a dual model, essentially. Discrete life, great, let's not drop that, but let's add to the storyline this idea of sustained life, so that we have an alternative worldview that recognizes the integration there. Another thing about life, and this gets on the idea of the mechanics that was mentioned in the introduction. If we go all the way back to where the machine metaphor really started from, most likely it would have come from Rene Descartes' work. Not really blaming him, it tends to be the followers of the geniuses that corrupt the ideas, but Rene Descartes is the beginning of the Cartesian worldview. And his famous saying, "I think, therefore I am," was starting to put into place this mechanical perspective that we have. And so this is really again the founding of the Cartesian worldview. And again, another great quote that's here. Actually, my screen is blocking some of the top of it, but you can see what I can't read the first sentence to you, but it's about how, to Descartes, that the material universe was what started to become the dominant paradigm, and that it provided a scientific sanction for the manipulation and exploitation of nature that became typical of modern civilization. Because if it's only a machine, you can tinker it with it in a way that you take it apart with the expectation you can put it right back together again. But as was later said, it's been successful, but the problem is that many scientists, encouraged by their success in treating living organisms as machines, tended to believe that they are nothing but machines. This is actually a quote from Fritjof Capra and Luisi's recent book, Systems View of Life. I've just heard recently that Capra has another book out that I'm looking forward to, another great systems thinker that's contributed a lot. But the idea that when you have a metaphor, you have a machine metaphor that, it operates like a machine, your mental model is now that it's a machine. And that's where you can get into trouble, because if we treat the fundamental working unit of nature as a mechanism, again, we basically turn the world into the machine we picture it to be. And an example I found just recently was a composting unit here. I actually have one of these in my backyard. You put in your food scraps and over time you get soil, and they actually labeled it the earth machine. And I thought that was just how far away from that. Like, it's not even questioned. Like, the person who made this understands that compost is a very organic and complex ecological process, but they refer to it as the earth machine without any sense of irony there. And that just shows how deeply embedded these machine ideas are. And what's one of the unintended consequences of this metaphor is that what happens to machines? Machines run down, they break down, they run out of gas, they fail, right? They have this, this idea of global collapse that we have, I think, is partly driven by this machine metaphor that we have, because the reality is that's not what nature does. We need to recognize that natural living systems are very unmachine-like. They actually self-organize, they self-repair after disturbance, they grow, develop, and they improve over time. Like, at some point, maybe machines will be able to do that, and that's a different discussion. But for now, the machines that we have are not able to do these things the way that the ecology is. And some very good examples of nature improving over time are things like the oxygen atmosphere that has given rise to aerobic respiration and much more release of free energies from respiration. And the oxygen layer, which allowed then land colonization and so on, soil formation, water purification, and so on. That many different ways that we see over time that the planet had actually changed in a way that becomes more suitable, right? Almost a Gaian approach there. So, we see win-wins out there where it's not just things running down and breaking down, but things improving over time. So then that takes us to if nature is doing it and has addressed, or if not solved, these problems, how can we learn from nature? So I would even say a lot of my research now is focused on this idea of ecomimicry or just understanding ecological principles and trying to apply those to our human social economic systems. And one of the things that we can learn is, again, maybe another Gaian thought, is that coevolution is really happening at a global level. We're dealing with some planetary feedbacks that have been changing the planet over time and in a way that I said actually benefits life, or at least the majority of life. There's always some trade-offs. I talk about that more later with my specific examples. And we actually live in a world full of life, right? So wherever you look on this planet, there's, if not direct life, there's definitely signs of life. And one of the other campaigns I'm on these days is to eliminate the word abiotic. Abiotic essentially means without life, abiota. And so you oftentimes hear people talk about biota and abiota. And I don't really know what they're talking about when they're talking about things on this planet that are without life, because you take a measurement of ocean pH. Well, that's what it is because of the carbon cycle and the photosynthesis and everything else that's going on, or humidity or soil chemistry. Every one of those seemingly abiotic properties is actually influenced by the life on this planet. So on a living planet such as Earth, we really should be referring to things as conbiotic. Even our technical physical measurements are influenced largely, or if not largely, in some sense by life. So I've been promoting this word conbiotic as an alternative to abiotic to more accurately represent the integration that this planet has with life. So if oxygen is a win-win situation, let me give you another example. Joseph Priestley is the scientist who discovered oxygen in 1774, and he did it by some straightforward experiments by enclosing something that was consuming oxygen, and then realized that it would extinguish itself because once the flame had consumed the oxygen, that it could no longer sustain itself. But where does the oxygen actually come from? Again, it's not always been in our atmosphere, but it came through the photosynthetic processes. Trees are the lungs of the planet, and as this picture is showing, we are cutting down our lungs, cutting out our lungs maybe too quickly. So he repeated the experiment. If you add plant material that's generating oxygen, you can have a sustained system where you can have the combustion and the photosynthesis each in a cycle. He repeated the experiment. I don't recommend you do this at home with another discrete life living organism. And over some time, the mouse and the candle both run out of oxygen and they both get extinguished. And in this case, since there's more consumption of the oxygen, you need to put more plant life, but you can understand how you can have a terranium that could essentially be self-sustaining. And at the planetary scale, clearly we have that because the oxygen that we're breathing in is coming from plant life. And one of the things that we are then proposing is, so I'm trying to see if I still have something at the top of my screen that won't disappear. Anyways, okay, I guess I won't get it to disappear. Is that Rene Descartes' famous saying is really discrete thought. if we come back to this analogy of discrete versus sustain, that it's about one person thinking one thing, one time and so on. And we're proposing, instead of that, this idea that I think, therefore I am, but going on, that is, I think now, therefore I exist now. But I think only as long as I have a steady input of oxygen, water, and food to sustain my thinking via my life. And after I'm done thinking, with the aid of these vital materials, they are transformed and expelled, not so much as waste, but as food for the plants and other living beings that in turn create and supply my material needs. I think, therefore I am, we are an ecosystem, right? So the quote from our book is making the point that really sustained thought only occurs because we are part of an ecosystem. We need the inputs and we generate outputs, and right, we're part of this cycle, the difference between just the fragmentation and the integrated worldviews. Okay, one last example of where I think the arms pathology is prevalent is in our thinking about sustainable development. It's very common to refer to these three equal pillars of sustainable development, that you need to have environment, economy, and society all working together in some sort of Venn diagram display, and sustainable development is right in the bullseye of that Venn diagram. And I understand what people are trying to convey with this message, but the idea of a Venn diagram is the interesting thing is the points of overlap, right? And so my question to any student or anybody really is, what is out here? What could possibly be in this part of the Venn diagram where you have something that is in the economy, but is not part of society or part of the environment? Right? There is nothing. I mean, I challenge you to give me an example, but there is nothing. You cannot have something that's, you don't have an economy without a society or without an environment. So why demonstrate a very large circle with all this place that is basically empty, and so on, right? So there must be a better representation. And really it's, I'm not discovering this, but it's the idea, it's nested hierarchy, that at the base you have an environment. Everything is that planet on which things occur. It's the space, the place that we interact. A subset of the environment is human society and all of the things that we do, but everything we do is not economic. We have a lot of kinship and friendship and other activities that are not just economy. So within the human society is another subset, which is the set of economic activities. I think it gives a very different picture on the scale and the hierarchy of how things occur. Not the economy is this big bubble out there under which it's equal with the other ones, right? It's really a subset of those, and I know that's a difficult message also to communicate, but I think it's a more accurate one. So we have these wonderful SDGs, which are aligning our global efforts on how to improve well-being for people across the planet. And there may be flaws in them and how they've been thought about and organized, but it's great that there are at least these organizing frameworks that we can be working towards. But again, they were put together in some sort of almost fragmented way or unequal way. And I've seen other people present them this way, which is the nested hierarchy view, that at the base you have the ecological factors, the biosphere and life on land, life on water. You have some that are dealing with society, and then some that are dealing with the economy. And again, kind of recognizing that if you don't have the base right, it doesn't matter how just things are or how prosperous things are, because the base is falling out below you. So again, the more holistic view recognizes those interactions. Another point I'll make about sustainable development, and there's this wonderful, almost a textbook definition of sustainable development from the Brundtland Report that refers to development that meets the needs of the present generation without compromising the ability of future generations to meet their own needs. Wonderful statement, consensus building. Everyone can agree that that's a beautiful aspiration that we should work towards, but it does a lot of the heavy lifting by kind of ignoring and packing into that word needs without really defining it, right? Whenever you start to get into the details, then there can be disagreement, but as a broad message, it's fine. So I view sustainable development as our needs, the human needs, is very anthropocentric approach towards this. And again, that we should be doing that, right? That makes sense for humans to think about the needs that they have and how we satisfy them in an environmentally sustainable way. But that's a different question than sustainability. And again, one of my points is that the words and the phrases are almost entirely used interchangeably. And I try to reserve the word sustainability for a more general system science kind of concept, which literally just has to do with how does the system endure over time, any system. It doesn't have to be a human system. It could be a completely ecological system. I'll give you some other examples in just a minute, but hopefully you see the difference. The first one is very much an anthropocentric concept, how humans develop in a way that allows them to keep developing. But the other one is just at the core, like is a scientific question, like what makes a system keep going? What are the properties? What are the energetics, thermodynamics, chemistry, processes, and so on that allow any system to keep going? And that could be something like this, right? This system is a sustainable system for several weeks. There's a pattern, there's organization, and there's energies and dissipation going on. So understanding how that's sustained, or maybe at a shorter time period, we get these kinds of systems, tornadoes that are very intense, but again, there's clearly a pattern, there's clearly processes that are contributing to that. You wouldn't think of sustainable development in terms of a tornado. In fact, maybe quite the opposite, but as a scientific question, how does a tornado sustain itself, right? That's a cool question to ask. Or what about Jupiter's anticyclone? We know it's been around since at least Galileo observed it 400 years ago, the great red spot, right? In fact, there was just some recent news about it that it's much deeper than they had thought, and it's able to sustain itself through energetic processes and so on. And clearly there are no humans involved in that, but it's an interesting question how it does that. Now, ecosystems have been around longer than humans, and that's also a good question on how they sustain themselves. Nowadays, as I mentioned, though, there's probably not an ecosystem on Earth that isn't impacted by humans specifically, but we could be looking at socioeconomic systems like cities, how they sustain themselves as, again, complex adaptive systems, or maybe even universities. I guess many of us are at universities or research institutes, and that's at another scale, a system that has flows and energetics and so on. So the question is, yeah, whatever scale you're dealing with, how do you make sense of the sustainability there? And here's my model of a sustainable system. It actually seems like a toy model the more I talk about it, but I think there's some insight here. The first requirements are that it has reliable inputs and healthy outputs. So you're dealing with renewable inputs, ones that you can count on over time. Again, ecosystems have evolved with solar radiation, which has been a very dependable source of energy inflow. And the idea of healthy outputs is that whatever you generate cannot exceed the assimilative capacity of the local environment in which it's doing it, or else you will run into some negative feedbacks that way. Then what's going on in the system is the other big question that I've been trying to explore, and that's something is going on that is using those flows in a way that's able to keep it sustained. It's not just taking it and kind of blowing through it and done with it, but it's creating self-organizing configurations through the use of autocatalysis, basically self-catalyzing processes that are coupled and overlapping at different scales. And that's what's going on in that system. That's what I'm interested in trying to understand better there. And it includes recycling of material, but also includes the processes be functionally linked together, such that the activities are integrated in a way that they're almost seamless, right? That you're creating material cycling, but only in a process linked way. I can explain that more later if anyone has a question on it, or please read our book, either way. But I wanted to leave some time for some of the case studies where there's kind of a divide between the theory and the case studies, and we're working on that. But my techniques that I tend to use are network analysis based approaches, and I've had a couple students recently looking at food, energy, water nexus, and I thought those would be relevant for this audience. So let me start with the study that was led by Saiga Vong, who was a Weiss's peer at IASA. And she looked at the energy water nexus under energy mix scenarios using input output and ecological network analysis. It's published recently in Applied Energy. And she was looking at energy for water, but also water for energy. right? You understand that you need energy in order to supply water, in order, to pump the water, to clean the water, and so on. But you also need water for energy because steam generation plants use a lot of water as well too. So you can break this down into those two questions: the energy for water and water for energy. What she was doing was building network models based on the sectors of the Chinese economy, and tracking then the embodied water that was going from one sector to another, whether it was for energy for water or for water for energy, and then coming up with different scenarios to see where there were perhaps maybe some trade-offs or some key insights, right? So the particular model that she was using had 30 sectors. This is fairly standard input-output table available data. And so things like agriculture and mining and petroleum. So the first few are very heavy resources: manufacturing, sawmills, paper, all the way down into electronics and scrap and waste, electricity, construction, and so on. So these were the different sectors, largely from the industrial manufacturing side of things. So domestic services shows up there as 29, and then other is everything else that is all the other social services, I guess, lumped into 30. And being able then to generate for each of those sectors how much of the energy was used directly in the sector versus how much was water related energy. And you can see that in some of the sectors, particularly some of the ones that have to do with like metal melting and mineral products, can have quite a bit of water related energy that is embodied in the use of those sectors. And then on the other side, in terms of the embodied water, that she was looking at 5 different climate scenarios, essentially, to see which ones would have the most, in terms of the energy mix of the society, which one would have the most embodied water. And again, there's a few sectors that really stand out in terms of having the most embodied water in order to produce the energies that would be needed under those different scenarios. And then there are these very nice, colorful diagrams that can be generated to show how the flows from one sector to another are. And in this case, this is again embodied energy. And as I mentioned, that this 13 is the metals, metal melting. And so it's the largest amount of embodied energy is going to that one. And the largest flow is this one, which is coming from this compartment, which is mining. And that kind of makes sense, right? That mining is giving a lot of embodied energies to this metal smelting. But you can track some of the other large flows coming in to this sector as well too. But a lot of information packed in that particular figure. So I just highlighted the largest one. Same thing with embodied water now. What you see here is, again, maybe it's not surprising, most of the embodied water is coming from agriculture. Nice result that confirms what we already know about that. Interestingly, though, that the largest amount seem to be going to the chemical industry and paper. That's this flow here. So yeah, so that's a way of tracking through the embodied energies and embodied water. And then lastly, what she was looking at were these trade-offs. So what is your policy? Is your policy to have the best water system, or is your policy to have the best carbon emissions, reducing greenhouse gases? And what was interesting was that this one scenario that actually had the lowest carbon emissions and total energy generation is this blue line, the dark blue line. And so if you were just going strictly for the carbon solution, you would probably pick that, but you see it actually has higher energy related water consumption and puts more pressure on water and so on than this gray line. So the gray line is slightly worse as far as your emissions are going, but it's much better in terms of your water. And so in the end, there's going to have to be a policy decision, right? Do we want to have, kind of an optimized solution, perhaps, where we are considering multiple variables, or we're just going for the greatest carbon emission reduction possible? In the conclusions of the paper, she was promoting the one that might not have been best in each case, but was more in the target of that, which seems to make sense. Okay, then let me give you one other case study which is also by another wisest peer, the same year, in fact, Nemi Vora. And she was looking at a trade, food trade, particularly grain and meat trade in the United States. And she was really looking at a food energy nexus, food energy water nexus of all three layers, and looking at how much embodied water and energy shows up in the food trade, right? So that's how all three layers are there. And in fact, what she did was a very interesting layering of the different networks, such that each one of these, so this is just a simplification of it, but imagine you've got a 51 by 51 matrix, basically the 50 states plus Washington, DC in the United States. And there is a flow of grain from one state to another. This actual would represent mass of cereal grains going from state to state. And on top of that, so you have a certain network, right, of the grain trade. And on top of that, you could have embodied water that is in the grain that is being traded. So how much water is being used through irrigation? It was only irrigated water. It wasn't rain fed. So this is additional water inputs that were used in order to grow those. So when you're trading grain, you're also trading embodied irrigated water, right? You don't see it, but it's there that can be tracked. On top of that, then you have embodied energy, because to irrigate the water, you had to do some sort of pumping. And then, however that was done depended on how much emissions you had. Were you using electricity that was from hydro plants? Were you using diesel? Were you using what other methods? So the fourth layer then was how many embodied greenhouse gases came. You know, all you wanted was a ton of grain, but with that came greenhouse gas emissions, energy, and water, right? So that was the idea here with her project. And in particular, she used a very interesting, fairly new network method that was looking at the maximum indeterminacy model. So this was the actual grain trade network model, similar to what I just showed. These are each of the different states and the trade that they have going to each other. What's interesting is that most of the flow is actually a self loop that you see here, which means most grain that is grown in each state is used within that state. That's actually, you know, again, not an uninteresting result, but and these are the states that have a lot of grain production, and the state that actually is importing the most grain of any of them turns out to be Texas. So I'm going to focus on Texas. Texas has a lot of cattle feedlots, which is why it imports so much grain. So this idea of the maximum indeterminacy model, or sometimes referred to it as the null model, would be how much grain would be flowing from one state to another just based on how much each state produces, how much each state needs, and then if there was essentially an equal weighting of all those flows, like nothing else was known about the system, and it's actually a zero information system because it's the most probable event if nothing else is going on. So you get these nice pictures, but essentially it's a way of comparing then the difference between these two. And we call this PMI, or point-wise mutual information. So I'm going to refer to PMI in the next couple of slides. And if you look at the virtual water trade network that she had constructed, and you look at the PMI, that what it shows is that a positive PMI indicates a higher than expected dependency, that there's more trade than would be expected in this neutral model. If it's a negative PMI, it means there's a lower than expected dependency. And the scaling is that the darker ones are the more positive, and then as it gets lighter, they're more negative. And there's some that are missing some data, but the ones that are pure white, I think, are actually missing data. But anyways, what you see is that Texas is getting most of its grain from itself and from its near neighbors, Oklahoma and Nebraska here, more than would be expected based on the neutral model, but not as much, you know, really from some of the more distant places. So clearly there's a gravity model going on as far as the trade is concerned. But notice that Texas is situated right here in the middle of the country, which is dependent on the Olagala aquifer, which is heavily utilized and being, you know, mined and depleted much faster than it's replenishing. And so the other states that are supplying grain from it are also using the same aquifer. So they're really all sucking down the same source, and they're using largely groundwater. So this is scaled by the amounts of virtual water. And so you see large amounts of groundwater withdrawal in these central plain states, and it's largely coming from this this really endangered aquifer. So that's the water perspective of it, right? And so now let's look at the energy perspective, which then leads to the emissions. And here's the fuel mix that the pumping can have. And so again, we can calculate how much emissions there are based on that. And the size, again, is scaled by the amount of emissions per cubic meter of water that is pumped. So some states, and again, these central plain states actually have a lot of emissions per water use. And so, other states can have quite small amounts of emissions because they're either using more hydroelectric or cleaner energies to do that. But again, you notice that the PMI values tend to be higher here. So there's overdependence on these areas that are close by, but also have high water depletion and high emissions factors coming in. So in the end, there's a trade-off, right? That Texas's grain trade is relying on unreliable inputs, and it generates unhealthy outputs. So it's clearly not sustainable the way that it's continuing to do that. And so maybe one suggestion would be to consider, a state like Montana that actually has more grain available to be traded and has a much lower footprint in terms of the greenhouse gas emissions. So, but again, the conclusion of her paper was, the science can give you these scenarios, but it's really going to be up to the policymakers of society to decide on the trade-offs and how the weighting goes in terms of, when you have multiple policies or multiple options on how to proceed with policy. Okay, so some conclusions. How do we balance our arms paradigm, our reductionistic mechanistic paradigm with holistic life science? We think that's part of this change, and that involves using systems thinking and ecosystem thinking and networks much more than we do already. Trying to find solutions that address the root cause of environmental problems and not just treat the symptoms of the problems. And that involves asking the two very basic questions: where does stuff come from, and where does it go? Like, we're all part of these large cycles. We are interacting with them on a constant basis, and an awareness, I think, is very powerful, right? So it's about seeing connections and making the connections of yourself and those around you. And some last parting words, care about yourself and care about your place. If we invest in these and make them better, that's really the best we can do. So I'm hoping to get more and more people excited and eager about these different topics, and we can explore them and discuss them, and maybe start to implement some of these ideas. So, all right, well, thank you for your attention. And I'm just ending with the last picture from the book that talks about how we can integrate across scale these different social ecological concepts. So with that, I should stop sharing. I think I'm pretty much on time. And if there are any questions, I can take those.
Thank you, Brian. It was one of the most enjoyable talks of the series, I may say, and it was a wonderful talk. So I'm going to abuse my position as the moderator and have the first question, maybe. So at the beginning of your talk, so you talked about how Descartes started this machinistic sort of view, but where do you think that people started objecting to that? So you took the name of Donella Meadows. She worked with Jay Forrester, and so who are really the champions of the systems thinking, so to speak?
Yeah, excellent question. Yeah, and it's interesting because the Forrester models are the systems dynamic models, which are systems oriented, but also objective, object oriented modeling. And so and as a network scientist, I think of the same thing too. Like when you talk about a node in a network, that's an object, and that's kind of it's not completely a holistic view. I mean, you can make network models, so you're getting there. But the question about where did it start? Well, I think there's two things. One, there was always a alternate paradigms. I think the Eastern paradigm was always more integrated than the Western paradigm. And I wish I knew more about the Eastern paradigms. But what I read about them is that they didn't go down that path. And then within the Western paradigms, there was always heterodoxy. There was always the systems thinkers. My understanding is it's always been a minority view, but they've always been there. You can go back to Bernansky's work in the 20s. You can go back, Bateson, some of the other Macy's conference kinds of things that were happening in the 60s with von Bertalanffy general system theory. So there's always been this undercurrent of systems thinking, and clearly, like Meadows' work, I think, launched the modern movement of that. But yeah, that'd be interesting to just like look the history of systems thinking and to track that. But I don't think it just appeared as an opposition. I think it was always there as an undercurrent or as a minor perspective.
Yeah, so thank you for the answer. So let me just take out the questions from the attendees now. So one question we have, I'm going to read it out. My question is, when we say the ecosystem self-organize itself is generally not true because of the pressure on it. There is a debate of losing forest cover in Pakistan. I think there is need of optimal conditions to self-organize a system. Your comments?
Right. So, yeah, I was talking about ecologically in the absence of debilitating disturbance, right? So clearly we can interfere with the natural processes in a way that are challenging its ability to self-organize, and I think that's one of those clear ways where we can say things are not sustainable because we are interfering with the natural processes. And oftentimes, I think one of the best restoration processes is just to back off a little bit and let nature do its thing. Now, we know enough about ecosystems that we can probably encourage them wisely to start self-organizing again. But I would agree with the question that, yeah, if we are cutting the forest down and disturbing them in a way that they lose these processes, then that's a recipe for collapse of those local systems.
Okay, thank you. And so let me read out another question. So you talked about sustainable development practices, and the question is slightly tangent to, but certainly related to what the talk was about. So what sustainable developmental practices can we adopt to combat climate change consequences?
Yeah, I like that question, because at almost every talk I get the question, like, what can I do? What should I do? What can I do? And I recognize that a lot of my talks are coming at a very high conceptual level, and it's not answering the question of what I do differently. Maybe by the end of the talk, it made a little bit, I touched on those, but I think that it's investing in place, investing in your local environments yourself, making decisions that recognize the indirect impacts that you have and trying to reduce those as much as possible, living in a way that is more in accordance with you being connected to the system. And I know that's still a somewhat unsatisfying answer, but it's actually a question that we're trying to address. We're trying to organize a series of workshops where we're going to get, the idea is to have different systems thinkers together and say, what do you do differently now that you know as a systems thinker? And we're very curious to collect this set of responses and to see how knowing something about a system really does change individual behavior or not. And maybe that will be a useful guide for answering this question, because I'm often stymied by this question, even though I get it at every talk. And what should I do differently? But yeah, I think it's living locally, making choices that recognize the connections that you're part of. So.
Okay, great. So Dr. Abu Bakr, maybe you would like to comment on any questions or any comments on the talk, or you just wrap it up.
Oh, sure. I mean, I actually was wondering about one particular thing. So, Brian, you showed this input-output system kind of a perspective. And that actually intrigued me quite a bit, because when we talk about system theoretic properties, especially like, for example, stability, we're not talking about sustainability, but say stability. And to characterize that, there are usually two ways to think about it. Either as this input-output property, you bombard it with a number of inputs and see what happens at the output. And if things blow up, then you call this system as unstable. But then there are sort of alternate ways or equivalent ways where it is not really this input-output thing, but something very structural. Like for a linear system, that's the eigenvalues that you find in a certain configuration, or something like this. So it's really an inherent property. I mean, with respect to sustainability, once again, is it really a view from the inside, that's a structural property, or is it really a view from the outside? Like these the things that you mentioned, like the inputs being reliable and the outputs being healthy, or really is it really the configuration of the system itself? So it seemed to me that you were pointing to both in your figure chart. But what really is your finding or your perspective?
Yeah, that's a deep question that I guess I haven't thought about that either, in terms of like, if you're inside the system, do you know that you're sustainable or not? Like, can you know if you're inside, or do you have to be outside of it to observe it and see whether it's sustainable or not? Yeah, interesting. I would guess that it's an external perspective that you have on the system to measure if it's being sustainable. But it's, yeah, I guess if you're inside the system and things are unsustainable, you might notice that at some point. But I think you need to have the perspective of, just like in a hierarchy, at some level, you're going to jump out of that to look down and then make an assessment of whether it's operating. But you're right. If these were all sustainable systems, we wouldn't even have to ask these questions. They would just be, we would be in them and they would be running sustainably, and we could be, ignorant to that. But I like that question. I'll have to think more about the perspective that we have on it.
Yeah, and I mean, that came to my mind because you were mentioning work by people like Capra and others who actually had thought quite a bit about other things before they went into all this Gaia business and living systems. For example, they were looking at these quantum mechanical systems where the observer and the observed, they're coupled in a certain way. And if you take away the observer, then, I mean, who knows what's really going on? So, I mean, that really is very, very intriguing to me, that what are the origins of this systems thinking? I mean, were these the kind of questions that were driving these people towards envisioning, I mean, these sustainability like notions, or is it really something else? So, I mean, I just wanted to find out what, if you have thought about this, or one thing that one thing I may say is that even in maybe some of the papers that I've seen in your work with, like one of the papers that you wrote with Elena, I think, this compartmentalized model where you set up a network and then you compute some sort of an information-like metric to characterize the sustainability. That is very kind of a structural property. But on the other hand, this input-output thing, I mean, that is how usually people describe sustainability. The kind of work that, for example, I've done with Talha, that's more like an input-output kind of a behavior. That was very intriguing to me. That I mean, you have both of these pictures, and does that go back to these fundamental ideas as you were exploring this historical development?
No, it's great food for thought. I probably just sometimes do something also without classifying it, and I should be more aware of that. I'd love to continue this discussion at IASA some point over lunch. So hopefully we can do that. Yeah, great points. I appreciate it.
Salah, over to you. Yeah.
Okay. So with this, we are out of time, and unfortunately, we have to end over here. It's 7 p.m. in Pakistan, and yeah. So in the end, I'd like to thank Brian once more for giving us the honor of hosting him, and it was A lovely talk, and I would say a very nice way of wrapping up the 2021 series, because we've focused a lot on water systems, and it was very refreshing to just come out of there and also think about the other systems which house the water system itself. And thank you to all the attendees as well. As usual, the recording will be posted on the website, and if there are any questions which we were not able to answer, please follow up on email, and we'll route your question to the speaker. And with that, goodbye everyone, and Allah Hafiz.